In this video, I will go through our assemble playbook and try to explain what it is, how it runs, and what outcome it will achieve. Assemble is an automatic script tool. It allows us to dynamically deploy our system in a scalable way. By dynamically deployment, it means that by simply running the shell scripts, like in our case, the run first.sh and run last.sh, it will build and deploy our system automatically. The run first.h runs the assemble playbook with the main.yml, which basically describes what tasks assemble will run. And in this case, it will first initiate the OpenStack in MRC, Melbourne Research Cloud. And then it will set up all the required dependencies on each instances we have created here. For example, in this big tasks group, assemble will first try to, let me bring up the comment. It will first try to install pipe and OpenStack SDK in your local machine. Then it will retrieve all the images from your remote infrastructure cloud provider. In our case, it's MRC. And then it will try to create all the volumes, security groups, and instances based on the variables we have defined in our variable file. In this variable file, you can see that we have defined the availability zone for our instances and the specification for all the volumes, volume name and size for each of them, and all the security groups that need to be created so that our application can listen to requests. And here is the instances specification and like image, what image we are using, what key we are using, and what flavor we are using. Apart from all the standard OpenStack initializations here, I also added another task called post instances, which basically will retrieve all the instances IP address and add them into our inventory file, so that they can be used for our other playbook. After we initialize all the instances, we move from localhost to our remote hosts. Remember, in post instances, I have added all the remote IP addresses to this group in our inventory file. And in this big task, basically, it will set up all the dependencies on each of the remote servers. The first will add proxy so that the remote servers can listen correctly via proxy. It just copy this environment file to the remote file, and then it will mount the volumes we just created here. It will mount the volumes to the server to the virtual machine. Now, when we mounting the volumes, I choose to use XFS file system as it is well supported for large volumes. And in our case, our volumes are about 150 gigabytes, which is quite large. After we mounting the volumes, it will install all the required packages. Basic packages will be installed like Git, Python, and then it will install Docker, particularly, as all our application will be run inside a Docker container. After we install Docker, we also need to update Docker's proxy as well. We need to specify those two proxy file and copy them into the Docker configuration as well, which is done here and here. After that, we restart Docker to apply the changes, and that's all for the setting up stage. Now let's have a look at a demo to see how this assemble playbook can be run. And you can see here our project space is very empty. And before we run the assemble playbook, there's something you need to double check. First, you need to remember which key pair you are using. In our case, we are using the first tryout key. And then you need to download the OpenStack RC file and save the file in the project root folder. We download this file and rename it to OpenRC demo.sh. If you are using a different name, then you need to change those two shell scripts accordingly, as we need to source this OpenRC file, OpenRC.sh, before we run the assemble playbook. You also need to go to navigate the setting and reset your password and save the password somewhere, because you will need to enter the password when you run the assemble playbook. Yeah. Now let's have a go. As you can see here, you need to enter the password I just mentioned about. And I just enter the password, and now it will start to run those tasks. Now the assemble playbook is finished. Let's have a look at our project space. You can see here, the 3 instances have been created, and there are 3 volumes as well. The security groups have been created accordingly as well. Now let's have a look at our second assemble playbook. This run last.sh shell script basically runs our second assemble playbook deploy. In deploy, it will first copy our app project directory into our remote machines, and then we deploy CoachDB to the harvester and our app inside 3 different Docker containers. Let's have a look at them in detail. I will skip copy directory because it's a really simple task. Just using SCP to copy all the files. To deploy CoachDB, we have also used a Docker compose file, which is written in the templates module of assemble. And the templates module of assemble utilize Jinja 2 as the format as the template. In this template, I have defined which image to use, and the advantage of template is that I can use the variables I have defined for these tasks. And if I want to change them, I can simply change the variables file instead of changing the this file directly. So here I have defined coach image is coach 3, and the version is 3.1.1. And the Jinja will replace those 2 fields with those values. I have also opened up all those ports for later usage. The volumes are mounted from this directory to the Docker data directory. I have also set up all the CoachDB user password, all these necessary environment variables as well. And all of them are defined in our variable file, which is really convenient. And finally, let's move back to the CoachDB deployment. After assemble upload the Docker compose file to our remote machine, it will then try to run the Docker compose. And after that, after Docker is successfully running, it will retrieve the 3 IP addresses from our inventory file. And then it will start to set up the clusters. Due to some unknown reasons, the CoachDB will not automatically create the system required database for us. So here I have added some necessary check before we set up the clusters. I first check if the user database exists. If not, I need to add the user database manually. Same goes here. The replicator database may not exist. The global changes database may not exist either. After those databases has been successfully added, now I can the assemble start to set up the cluster. All the cluster procedure is exactly the same in the official CoachDB cluster setup documentation. They have been translated into assemble scripts. Now let's have a look at how to set up cluster in detail. Firstly, assemble will send a GET request to see if the cluster setup has already been enabled. If not, it will enable the cluster setup first. And then apart from the main node, the 2 worker nodes will need to send those 2 pull requests as as specified in the official HTTP class setup documentation. And then we send an empty message, get message to avoid some strange errors. And then we send the final finish cluster setup message to HTTP to finish up our cluster setting up. After HTTP is setting up, Assemble will run the harvester tasks and try to set up the harvesters inside our remote machines. As you can see here, we are no longer using Docker Compose to start a Docker container. Instead, we are just running a shell script. Because for the harvester or our web application, all of them are using our customer Docker file, and those Docker file needs to be uploaded to remote machines anyway. So we can just so instead of writing an additional Docker Compose file, we decide to just run the Docker file directly. And the run node and those three different shell scripts are basically running three different Docker files, and so that we can split up harvester regions. Like on node 1, we are crawling Melbourne, and on node 2, maybe crawling Sydney, so that there will be no duplicated data in our database. After those tasks have been successfully run, Assemble will run the deploy app main.yml. It will first upload the required data first, and then it will run the app application, run the app doc file, as in the same way we just saw to the harvester. And additionally, it will only be run in the master node. Now let's have a look at what's inside this run.sh. Inside this run.sh, it's a really simple shell script. It's just running docker build and docker docker run. Yeah. The Docker file looks like something. Looks like this. The base image is Python, and we have specified the Flask because we're using Flask. So we have also specified some Flask environment variables. We then copy the requirements into our directory inside Docker and try to install all the requirements. Yeah, we are using Flask REST1 requests, and that's all. Then it will expose the port. And if you remember in our previous security groups, we have specified the port 8003 is for app connections. And then finally, it will use the command to run the Flask. The same goes with all the Twitter harvesters. The Docker files are almost the same. Yeah, you can see here, they are almost identical, except we are not using Flask here. We're just using raw Python. Now let's have a look at demo to see how to run our second Assemble playbook. Before we run the playbook, there's something else we need to do first. We need to find our smallest IP address from our last Assemble results, and copy it and navigate to HTTP configuration.py and replace the IP addresses because our app will only be run in the main node, so we need to specify it here. After that, we can just then run our shell script. And you can see here, we need to copy the password again. Now the Docker has all been deployed. Let's navigate to one of the remote server to see if they are actually working, if they are actually being deployed. As you can see here, the CoreDB is still running, and our app is running. The Twitter harvester has stopped because all the data has been already uploaded and cloud. So since our CoreDB is running, let's double check if we can access the CoreDB from our local machine to see if the ports are opened correctly. To access the CoreDB, we need to just tap into the IP addresses and enter the port pipeline for utilities. As you can see here, the CoreDB can be successfully accessed from our local host. And to access our web application, we can use the same URL as via the application port. Yep, our web application can also be accessed successfully as well. And that's all from our sample site. That's all about our sample playbook and how it runs and what it achieves. Thank you.